Physics is quite prevalent in our daily lives, such as the example behind me. That's a gyroplane, or an amusement park attraction which spins around. And spinning is a concept of physics that's being applied here, specifically, concept of circular motion.
Let's simplify this first though. All circular motion, whether rotational or revolutional, is caused by a type of force called centripetal force. The thing about centripetal force is that its direction always adjusts towards a single point at the center of a circle, which is called the axis. This causes the object to be perpetually turning, keeping it going around said axis. Since the direction is always changing, the object is also always experiencing some acceleration, specifically centripetal acceleration, and has angular as opposed to linear velocity. This does not mean that the object cannot also have linear velocity. In fact, the two are connected. The angular velocity of an object experiencing circular motion with the symbol omega is defined by its linear velocity divided by the radius of its path. When angular velocity is already known, the object's centripetal acceleration can be found by squaring its angular velocity and multiplying the result by the radius of its path. From this, the object's centripetal force can be calculated as usual. Force equals mass times acceleration, though using centripetal acceleration instead of linear acceleration.
So from this, how do we determine the accuracy or validity of the equations we have shown before? Of course, we can use an experiment. This experiment will also confirm the value of gravity, as that is the real value we will be comparing.
To do this, we need a plastic tube with a string running through it. This string will have a stopper at one end and a weight on the other. A ruler of 30 centimeters is also required, although other lengths are also sufficient. A stopwatch is also needed to record the time of revolutions done. Other apparatus that are also needed is a triple beam balance or any other scale that is sufficient to measure the mass of the stopper and the weight on the end of the string. And a marker of visible color when it is used to mark points on the string is also needed.
Before starting, we must determine a mass we want to use as a control variable, and then measure that mass and the mass of the other stopper on the other end. Then, we measure different radiuses that we use as the independent variable. In this case, 10, 20, 30, 40, and 50 centimeters. After that, determine the number of revolutions you want to do, as we will record the total time needed for that number of revolutions and divide it by the number to determine the time needed for one revolution. This is done to maximize accuracy of the time needed for one revolution. In our case, this number is 20. When you have finished doing every step before this, then you can proceed with spinning the stopper around the plastic tube above your head as demonstrated like this. It is important to make sure that while spinning, the height of the mass and the radius between the stopper and the plastic tube axis is constant, where there is no changes in this length. Also, make sure another person is recording the time using a stopwatch, and another person is counting the amount of revolutions until it reaches 20 revolutions. Then we stop spinning. We then repeat this process with the different radiuses we have already determined before and obtain the time needed for 20 revolutions.
So here is our data. We have the masses of both the spinning object and the hanging mass, as well as the table from the experiment itself, which is the spin radius and the time of one revolution.
I've drawn the free body diagram of our system. Since the experiment involves a spinning object, the main force is of course centripetal force. In this case, that is essentially just the tension in the upper string, or T1. So, Fc and T1 are one and the same. Another force acting on the system is the weight of the object attached to the bottom of the string. We'll call that W. However, it is stated previously that the system should ideally remain static in the y-axis, so there should also be a force countering the weight in the lower string. We'll call that T2. Since both tensions are on the same length of string, they are equal. T1 equals T2. Thus we can say that Fc equals W. Expanding both sides of the equation gives us m1, which is the mass of the spinning object, times omega squared times r, the radius of the spin, equals m2, the mass of the hanging object, times g, the gravitational acceleration of the planet. Here we can see that omega squared is 1 radian per unit time, which can be expressed as 2 pi per unit time. Substituting this into the main equation gives us m1 times, in brackets, 2 pi divided by t squared times r equals m2 times g. Now we have to go back to our data. Before we can use it, we have to plot it onto a scatter graph. Here, the independent variable is r, which will be the x value, while the dependent variable is t, which will be squared first before inputting into the graph as the y value. Using the tools available in the spreadsheet app, we obtain this graph and a regression line with the equation y equals to 0.6578x. 0.6578 is the gradient, or m, of this graph, which is y over x, or in this case, t squared over r. You might have noticed that the inverse of the gradient, 1 over m, about 1.52, is r over t squared, which we have in our equation. Thus, we can substitute and rearrange the equation so that g is equal to m1 times, in brackets, 2 pi squared times the inverse of the gradient over m2. Inputting all of our known values into the equation and solving it gives a gravitational acceleration value of 10.5 meters per second squared. When comparing this with the actual value of gravity of 9.81 meters per second squared, our percentage error is around 7%.
This error could have been avoided by measuring a more accurate marks in the string and also being more consistent in making the revolutions while doing the experiment.
As our percentage error comes at 7% and it's still less than 10%, we can confirm that the value of gravity is 9.81 meters per second. And also, we can confirm the validity of the equations we have used before, as those equations are used in the calculations to obtain our value of gravity, which is still under 10%.